So we're now heading towards the second lecture of today. Can you please join your hands together to welcome Professor Kamil Adamezewski. Please quickly achieve and word of it. Okay.
Hello everyone. This is my first time presenting here. Actually the only one. So I'm very happy and proud to speak in front of you. Thank you very much for the invitation. And I hope you will take something away from this lecture. In the meantime, if you have any question, maybe shout out, because I cannot see you because of the light, but I want you to follow the entire lecture. So if you want me to stop, repeat something, just raise your hand or just shout out. I will not be offended. All right. So today's lecture will be a mixture of experts. In the program, it said about language vision models. We will focus on more on the general architecture, which is mixture of experts, which can be applied both for language and for vision. However, it's been extremely powerful and useful for language models, and that is what you'll be later implementing in the lab. So you will get your hands dirty with this algorithm, and at the end of the day you should be able to implement it and test it. But first I'll give you the theory and the overview, hopefully in an accessible way. So before I start, I just want to say, make a little bit of a mentioning of my future school. I was in ETH Zurich before. From next year I'll be joining a school in Poland, in the Wrocław University of Science Technology. And because the name is so hard to pronounce and nobody knows it and nobody remembers it, so I thought I'll mention it. It's a beautiful city in Central Europe. It's pronounced Wrocław, and if you ever travel to Europe, travel to Poland, I recommend you visit, and you can then also hit me up and we can talk there. I'll take you around. So that would be my future place. All right, let's get to the meat of the lecture. So, mixture of experts. Has anyone or who has heard about this term, mixture of experts? Can you raise your hands? I don't see, maybe a few. Okay. Mixture of experts, it's interestingly, we'll look at the brief history of mixture of experts. It's a quite old technique. However, it recently gained quite a big visibility with large language models. But let's go step by step. So in 2023, there was a new large language model released, which was called Mixtral 8x7b. So what does it mean? What is 8x7b? For those of you that you know, and if you don't know, I will kind of solve this little mystery during the lecture. So keep that in mind that there was this model which was coined as Mixtral 8x7b. Then in 2024, actually during a conference, the NVIDIA CEO accidentally, I don't think that he meant that, when he was showing this plot that basically plots the timeline against the training compute flops used for large language models, he accidentally put this naming for the actually new GPT-4 model, which was named GPT MOE 1.8T, which also displayed the number of parameters for the GPT-4 model, and that's why we have a kind of a broad understanding how big this model is. But it also had this naming MOE. And what is MOE? This is what we're gonna discover in this lecture. All right, so typical machine learning model that all of you learned, or if you even didn't learn, then you will learn now. This is the simplest modeling of a machine learning problem, where we have certain input. It can be image, it can be a text. Then we have a certain model, which can be a neural network, it can be a linear regression, it can be some clustering, some model, and then we will have an output. So this is what we've been learning all along, and that is the basic structure for a machine learning problem. So we will modify this understanding with this paradigm behind a mixture of experts. And perhaps you have heard about divide and conquer. You've heard it? Yes. Okay, so that is the key idea behind the MOE. If you have heard about divide and conquer, then you also heard about mixture of experts in a way. So divide and conquer, for those of you who have not studied it, it's basically dividing a problem into smaller, simpler problems, and then solving each of them separately. So instead of tackling a big problem, which might be hard to solve, we will tackle small problems, and by solving those small problems, we will solve a big problem. So it's a generally good advice for life as well. Like, if you feel overwhelmed, maybe you should just take it step by step and break these complex problems into simpler ones, like in MOE. So what happens in MOE? MOE also breaks the complex problem into those smaller ones, but adds something called gating, which basically tells us and guides us which of those experts we should use. We will dive deeper into it. This is just a broad overview of the method. That instead of a traditional paradigm where we have one model, in the mixture of experts, we build our architecture from different models. So we will have different models called experts, and then we will choose for a given task, for a given input, one of them. So we will have at our disposal a broader range of models. Some of you maybe also heard about ensemble modeling. This is also related. But in mixture of experts, we will have this routing, which will guide us which of those models we choose. So for example, here are a few examples where that could be useful. Perhaps we could, in the digit classification, the most basic classification problem, we could have one expert which specializes in digits 1 versus 7. They are similar, and maybe there should be one that focuses on this problem, or another is 3 versus 8. With the whole model to actually tell us, we don't need to use the capacity of the entire model. We would like to have a specialized expert that will basically tell us the solution to this problem. You can hear me well and see me well now? Is that? Give me a shout. Okay, perfect. Thank you. Great audience. Okay, so these are the examples of these specializations. Of course, these are simplifications. I mean, in reality, it's not exactly like this beautiful. We will basically, those experts will be learned and they will have some specializations which might not be as interpretable, but generally this is the key idea behind the experts. So in NLP, for instance, there could be experts for a question, another can be for statements. In computer vision, maybe one for low resolution images, another one for high resolution images, multitask, then basically we can divide it between different tasks for text, image, and audio. These are the ideas behind the mixture of experts. Okay, so how a little bit of how it came into being. So that it derives, as I mentioned, from the idea that we have multiple models, which can be like called weak learners as well, which are maybe they're not that great, but together they become a strong predictor. The original work dates back to '91, but that is more about an idea rather than the implementation, because at that time the computational limitations stunted basically the growth of AI and didn't allow for the scalability of this problem. We came back to this idea of mixture of experts in 2017 in the work that applied mixture of experts to LSTMs. So perhaps you have heard LSTM, the idea about LSTM. That was kind of a precursor for the transformers. It's a type of recurrent neural network that was used in natural language processing. This work really was the first one to apply a mixture of experts to NLP at large scale, and it showed that it's possible to build very large models thanks to the MOE. And then, following this trend, there was another work that basically applied it to the transformers, and that is what we will be focusing on today, on applying MOE to transformers, how it is implemented and how it works. So that is the short history, but as you saw, all the more recent models they have their MOE versions, and it's become a very popular paradigm. And why is that? We will see. All right. So transformers. I will just briefly go through that so that just everybody's on the same page. But I'm glad that yesterday there were a few lectures that went into details. So you should be familiar with the dense transformers, as we call them, compared to the sparse mixture of experts. So this is again a revision of the architecture of transformer. So that we will build on top of it to understand how mixture experts is implemented. All right. So as in a regular transformer, we will have tokens, because this is an example of an NLP. We'll also look at vision a little bit later. So the input tokens are fed into the model. Then we will have self-attention, which consists of query, queue, and value. And then we will have a feed-forward layer with some residual connections and layer nodes. Right? Okay. Inputs. Then we will have here decoder blocks, and they basically connect. Each decoder block consists of attention and feed-forward layer. And then we will basically stack these decoder blocks to get the output. All right. So here are a few elements of the transformer layer. If you know, you can shout. If you don't know, you can try to guess. when we will be dealing with mixture of experts, we will be basically working in particular on one of these components. Can you guess which of these components of the transformer will be most relevant for us in mixture of experts? Try it. There are not many chances. Feed-forward network, I hear. Yes, this is correct. So we will be actually replacing a feed-forward network with so-called mixture of experts layer. So this will be the key component of the transformer that we will be working with. The others will remain the same. So that's why I said that we will be building on the current architecture of a transformer. So this is an FFN layer, and this FFN layer is in general in transformer. This is the biggest layer, in terms of the number of parameters. So it stores basically the most parameters. It stores, we can say, the most factual knowledge, and it directly affects the model performance. So if we are talking about the millions or billions even of parameters for a transformer model, then most of the parameters come from those feed-forward layers. They are very heavy in the number of parameters, and this is where we're gonna basically that's what we're gonna target when it comes to the mixture of experts. So digging a little bit deeper into FFN layer, the typical FFN layer in the current transformers is basically a two-layer network. It's a two-layer MLP, which, as you see, it takes an input of the size of, like, it's called D model. So this is the dimension of the network. It's a bit wider in the middle, and then it will converge again to the D model at the end, and then it will be passed on to the next layers. So this is important when we will go later at the end. We will talk about how actually we can divide it, this middle layer, into some fine-grained experts. But don't worry about it right now. So this is a typical FFN layer in a transformer. So since we're now familiar with transformers, we're familiar with the FFN layer, then let's dive into the mixture of experts and how it is applied in transformers. So in transformers, each FFN layer can be replaced with an MOE layer. And this is the key, basically the key difference that makes mixture of experts work for transformers. So instead of one FFN layer, we will have 4 or 8 or 16, or there's even some words that scale it up to millions. But we'll not go. I will briefly mention it at the end. But the possibilities are basically endless, and but the most typical values are about 8, and that is kind of the practical value used in the industry. And originally, most typically, each of these FFN layers is basically a replica of the original one. So they are basically of the same size as the FFN layer, just they are multiplied, so they are bigger. And as a result, basically we do have bigger model. You may ask where the efficiency comes from. We'll go into it, and I'll show you why everybody uses actually mixture of experts despite them being bigger. So MOE layer consists of three elements. The first one is experts. So experts are the FFN layers. They correspond to the models that in the beginning I was telling you about that. We have instead of one model, we have several models. So in transformers, we can say that instead of one FFN layer, we have several FFN layers that we can choose from. Then the key difference between assemble methods and other similar approaches is the router, or sometimes called as gating. So gating is a small neural network. It's our helper. So it costs very little, but it tells us actually which of the experts we should be able to we should go to. So we are basically not wrong, or we don't want to go to a wrong expert. We need to have some kind of guidance, and that guidance is provided by router. And we'll go into more details about router a little bit later. And then at the end we will have the combination mechanism. So we will select certain experts, or should we select all experts? And that is the question for the combination mechanism that we will answer. So mixture of experts layer contains of these three elements: experts, router, and combination mechanism. Are there any questions? For now, we're just covering the basics. We're good. All right. Okay. All right. Let's go. We will have. I will try. Oh, yes. Yes, then.
So it's always necessary to have this after the compute.
It's always necessary to decide after you do the computation, these 8 different FNN blocks, or you could actually do beforehand. Maybe if you could decide which all experts to feed into, then your number of computation would reduce, right? Then would that be possible, or that will not make sense?
You're asking whether it's possible to choose experts before.
Yeah, so the gating mechanism would tell me which experts to use before I do the compute instead of after doing the compute.
Exactly. I mean that is basically the key. That is the key of the mixture of experts. That the cost of the router is small, and we will just perform this computation to know which of the experts to choose. And then the big computation will follow only for the selected experts. But I will go into the details when in a moment. But yes, that is the key basically behind the mixture of experts.
All right, thank you.
Okay. Perfect. A moment to wake up.
Anyone? Any questions?
All right. We'll have more opportunities. All right. So let's dig. Okay. Let's dig deeper into what each of these elements are. Okay, experts. So it's a set of submodels which are fully. In theory, they can be anything. They can be fully connected layers or convolutional layers, other networks. In the typical transformer, they are FFN layers. And then each expert specializes in handling a specific subset of the problem or input space. So for M experts, we will just identify them F1, F2, and so on, Fn. All right. So Is that, let me just check what is, okay. So now we get to the first solution of the evening or afternoon. So I asked you in the beginning what is the mixture? 8 times 7b. So based on this, you probably suspect that this is a mixture of experts architecture with this special naming. So can you tell me how many experts are there in this model? Exactly, there are 8 experts. This has been, as I said before, most typical value used in the industry. This naming is a little bit misleading because it says 8 times 7b, so that would mean that we have 56 billion parameters. It's not exactly true. We have actually less of them. And why do we have less of them? We have 47b. We have less of them because, as you saw, in the transformer architecture, we only repeat the FFN layers. While in other elements, like attention or layer normalization or embedding layers, they are shared. So in practice, we don't have completely separate transformers. This is one model that consists of just several sub-elements, which are the feed-forward networks. So as a result, we have actually only 47 billion parameters instead of 56. And I think I didn't mention it in the beginning why there was such a buzz about mixed RAM. It was because this model actually outperformed a much bigger model. It was Llama 2 with 70 billion parameters. So a model with only 47 billion parameters outperformed a model with 70 billion parameters. And that was not the end. And we will see later that even this 47b, it's more than actually it is used. In practice, we use many fewer parameters, and we will see why. So that is what happens in the broad picture of the mixture of experts. We will have several of the experts, but we will only activate some of them. In this case, you can see that although we have 4 experts, in fact, only the activations go through one of them. So keep that in mind. This is basically the key saving mechanism in the mixture of experts. So how do we choose which experts to choose, or how do we weigh those experts? This is the second element in the MOE architecture, which is gating. So as I mentioned earlier, gating is a small network that will help us appropriately choose the experts. So this gating network assigns weights or probabilities for each of the experts. So it's a typical small one-layer neural network, which ends basically with softmax layer, and it assigns probabilities to each of the experts. So if there are 8 experts, it basically will have the output dimension will be 8, and it will output probabilities for each of them. So this is our gating mechanism, and then the question is, how do we make use of this gating? It's through the combination mechanism. So in the original approach, there are several ways how we can approach. So in the original one, we will have a set of weights at the end, and some of them will be higher, some of them will be lower. So one way of taking advantage of several experts is to weigh them, because maybe for one input, one expert is important,
And maybe another one will be also important, but not so important. Say there will be 0.7, 0.2, 0.1. So we will weigh each of these experts by the value that is given by the gating mechanism. And that is basically what we see here. That we have the value for each expert. Those are the activations for each expert, and then we will have the gating mechanism, which will basically multiply the probabilities by basically the weights of the expert. So as a result, we will have basically weighing of the experts. But the question is it more efficient or not? Who says it's more efficient like that? Who says it's not efficient? Okay, that's right. It is really not that efficient because we will have a lot of experts. Okay, we can have we will have a better guidance because we will take advantage of the knowledge of each of the experts. But computationally, that will cost us a lot because we will have to really run each of those experts. And that will be very costly. That will be as if we had run instead of one model, multiple models. And that is not ideal. That is not something that is even feasible. So people came up with another very simple solution, which is top K. So basically, instead of activating all the experts, we will activate only some of them. And depending on the paper, the original one activated 2. More recent, it's been shown that 1 is just enough. And as a result, instead of basically, we will have at our disposal 8, 16 experts, but we will activate only 1 or 2. So here's the difference between dense MOE and sparse MOE. So in dense MOE, we will still have gating with all the weights, but we will weigh each of these FFN layers by this weighting factor, but we will run all 3 of them. Instead, in the sparse MOE, we will only choose 1 or 2 of them, typically, and this one, it will be just there, but we will not use it. So computationally, we will save the computation from this one FFN layer. So this is the key behind the sparsely gated or sparse mixture of experts. So this is an example of top 1, where we only choose 1 of the FFN layers. This is an example of the top 2 routing, where we choose 2 of them, etc. Okay, how are we doing with time? All right. Okay. So as a side note, I don't know if you noticed, but I'm sure you did, but I just want to emphasize it. Basically, what happens is that for each input, we will activate a different set of experts. So we will have maybe 8 of them, but for a token walk, we will activate the first and third. And then for the token is, we will activate second and third. Which is quite cool when you think about it, because the network adjusts to the input. And the network allows us to conditionally select parts of the model based on the input. And this is the paradigm called conditional computation. It's a broader paradigm, that mixture of experts, and it basically tells you that you can condition based on the input. You can condition model based on the input. It's a very efficient way to actually save computations, because perhaps you are familiar with other methods for efficient AI, such as pruning or quantization. These methods decrease the size of the model, but that model, in a compressed way, is used for every input. So it doesn't matter whether this is what, whether this is this, whether this is dog or is it a cat. Like there's the same network that is used for all the inputs, which, when you think about it, might not be that efficient because the model contains a lot of information about everything. And when we want to classify whether it's a dog or a cat, we probably don't need the information about a car and about what food, I don't know, is favored in Nepal. So this is again a broad paradigm which is called conditional computation. I just want to, as a side note, give you one example of another example of conditional computation, just so that you have like a broader understanding of the field and maybe you can better connect the dots. Perhaps you've heard about early exits. This is completely a side note, which is not related to the mixture of experts, but just want to mention it so that, again, you have a broader picture. So early exit methods is another example of conditional computation. This is a convolutional network with several convolutional layers. It could be also a transformer with several blocks. And what happens here that we normally in a typical network we have a classifier at the end. But in the early exits we have classifiers after each layer. Because perhaps for some inputs which are very easy, like say this giraffe, like we clearly see that this is a giraffe. We don't need really the power of the 32 stacked layers. Maybe after one or two, we will know that this is a giraffe. So after each layer there is a classifier that will basically tell us if it will give us again a confidence. Will give us softmax confidence, and if this confidence is high, we can actually exit earlier. So, and if we are not confident enough, we'll go to the next layers. So this is called early exits. Maybe some of you are familiar with it. If not, it's also a pretty cool approach. It's another type of conditional computation algorithm in a similar way that mixture of experts is. Because in this case, we divide the samples between the easy and hard. And in the mixture of experts, we will divide the samples between specialized experts, basically. So we will choose maybe expert that is responsible for giraffes, maybe another expert is responsible for dogs, or so on. So, but again, for a given input, we will have a different subset, different submodel of the network that will be used. So this is in generally conditional computation. All right. So, but today's lecture is about mixture of experts. If you have questions about early exits, feel free also talk to me about it, or generally about other topics related to conditional computation or efficient AI. All right. So in an overall picture, the inference in mixture of experts. This is basically the key for the efficiency in the mixture of experts. So to summarize, we will have tokens which will go through the shared layers, self-attention and normalization layers, and each of them will go through the router gating mechanism. And for each of them, this output of the router, softmax probability distribution, will be different. And based on this probability distribution, we will route it only to a selected expert. And then this will be processed here, and then we will follow to the next block. So that is how the inference is done in the mixture of experts. So at our disposal, we have a big model, but in reality, we use only
a small part of it. This is kind of a depiction of the entire model, because for each decoder we might have different experts. So perhaps for the first one we will have an expert 1 activated, then expert 3, and so on. So for each of the block there will be a different routing mechanism. There might be a different expert activated. But overall, if you see, the more blocks we have, the more savings we have. Because in this case we have 12 experts, but we only use 4 of them. So but at our disposal, if we actually computed how many possibilities we have. Okay, a question from the combinatorial theory. How many paths there are here that we can take? We have 3 experts at each layer, and then we have 4 layers. So, shout high, shout. 21? 81. Yes, exactly. It's 3 to the power of 4. So we have 81 possibilities for each input. So basically we have 81 choices, as opposed to only 1 choice if we didn't use mixture of experts. Because if we use just a dense model, we would basically have just a fixed path that we will follow. In this case, we have 81. So as you can imagine, some of those paths may be better, some of them will be worse. And the idea of the mixture of experts is to select the best path for each input. Exactly, it yields mixture of experts faster inference versus a comparably large dense model. Alright, so that was the inference, but training is actually also more efficient. So we will follow in the forward pass, we will follow exactly the same path as in the case of the inference, where the top case are selected. We will compute the loss. And in the backward pass, we will only update the weights of the selected experts. So we will not need to update the entire model. We will only update the experts which were selected during the forward pass. So training is also more efficient. All right. Okay. Are there any questions at this point?
So in that 4 expert case, if I do top 1, then I assume it's not going to be 4 times more efficient. In practice, what is the expected efficiency in terms of compute? Because I still have to load the experts, right? And the router will take some compute. And what do I expect? What factor do I expect in practice?
Okay, so we will see an example of the mixtral. I think there is one somewhere later, but generally speaking, if we have a small number of experts, for instance 4, 8, the cost of the router is negligible. So we consider it much smaller. It's a small MLP layer, so we don't take it into account. We will see later that yes, if we have more experts, that the cost has to be taken into consideration, and it will basically impact the performance. In terms of other aspects of the efficiency, the Mistral, which I mentioned, has 47 billion parameters. In fact, during the inference, there are only about 13 billion parameters used. So this is kind of the ratio of how more efficient it is during the inference.
That still assumes that I still have to load all the model, right? I just not perform the some of the computations.
Exactly. So this is a very valid point, which we will see also at
when we talk about the challenges of MOE. So one disadvantage of MOE is that we still need to load the entire model to the memory, and that is why there may be some reservations about using MOE. However, there are works. I don't know if this is already implemented, where basically during the inference we load the experts. But typically we have to load the entire model into the memory, and the savings are from the computational standpoint. However, this is an ongoing area of research, which I also do in my lab, and there will be some works coming out which shows that even taking into account the memory constraints, MOE is still more efficient than the dense model. Even if we basically taking the same size MOE model and dense model, MOE still is better. But again, this is an active area of research, which I'll be happy to talk more.
Okay, I'll keep my questions up till the end. Thank you.
I have one tiny question. I'm very curious about that. Is like how you make sure that all the experts, they are diversified, and how you make sure that your router is not just lazy and always pick the same guy. Maybe we'll come to that later. I'm sorry if it's...
Yes, a very good question. We exactly will come to that later.
Okay, then I will leave it for...
Yes, but I have a very perceptive audience. Are there
Any questions, guys? Do we have anyone? Just raise your hand if you have got any questions. I can read them back up to you. Okay, so we have got a question.
There is a question? Okay.
Hi sir, my name is Rubika Bashar. I was curious if we can fine-tune MOE models. As you said, there are many experts, so how will fine-tuning work on them?
How do we fine-tune the model?
Yeah, MOE model.
So fine-tuning the model is again more efficient, and it's quite convenient with mixture of experts. Are you talking about a model which is not mixture of experts, and we want to fine-tune it in a mixture of experts way, or generally speaking?
Generally speaking.
Generally speaking. So I mean, the training, the fine-tuning will follow basically the path that I showed you in a training procedure, where we will basically we will only select some of those experts, and as a result, fine-tuning is more efficient, because when you think about it, that we have only a few samples perhaps for fine-tuning. So in a dense model, we would have to update basically all the weights of the model, despite the fact that only parts of this model maybe are relevant for basically the samples are only relevant for some parts of the model. So mixture of experts is actually very appropriate architecture for fine-tuning, because if we have only a restricted set of samples, we will only fine-tune the experts which would be responsible for these samples, instead of the entire model. Another thing is that we also can add experts for fine-tuning, like the models. That's why they are, because of that, are more scalable, because we don't need to retrain the whole model. We can just add an expert, and we can only fine-tune that expert. So generally, mixture of expert architecture is very, I guess it's very prone to fine-tuning.
Anyone else? Okay, sure.
Okay, so let's see.
I have a question.
There is a yes.
Thank you for the lecture right now. So I have Since the MOA architecture is unique, I just want to ask, like, how does the strategy for like backpropagation and like gradient descent working for, like, it's kind of different compared to like original transformer.
You're asking how does the backpropagation is different from backpropagation from a distance transformer? Is that a question? Okay, so again, this is what maybe I went too fast a bit. Yeah. Okay, so the backward pass, the backpropagation, only updates the expert layers, the selected expert layers. So we only would compute the gradients with respect to the expert layers, and we would only update them. The rest basically doesn't change. So that is how the backpropagation is performed in the MOE.
Maybe I just have another question. So,
sure.
How does the computational are distributed on the hardware aspect? So, like, does it require a special hardware chip to operate on the MOE architecture?
No. There's no specialized hardware required. It basically works on regular GPUs. Of course, there is research about basically if the model is big, then we will have to divide it between the different GPUs. There are multi-node implementations, and but that basically is only related to the size. So, but if the MOE can fit into one GPU, then you can easily just run it on a GPU. And in fact, today during the lab, you will implement a small MOE that will be running just on the Google Colab GPU.
Thank you.
Let's quickly go. Okay, here. There was still some confusion about whether we need to evaluate all the experts, and the answer is we don't evaluate all the experts. So the way mixture of experts works, that we have this router. So this router gating mechanism, it's a small MLP layer. It's much smaller compared to the FFN layers. Say maybe if the FFN layer has 100 parameters, the router has only one parameter. Just this is kind of the ratio. It can be even more, 1 to 1,000. So the cost of the router is very small, and the router is always run, but the experts are not always. Only some of them will be. So at inference time, we will only run the input through this gating mechanism, which is a small layer, and that layer will output probabilities. So in this case, there will be some input, and we will have the output, which will be, say, 0.6, 0.4, and 0.6, 0.3, and 0.1. So that will be the output of this small router. And based on this, we will make a decision. 0.6, the first one, has the highest value. So that means that it is the most appropriate expert. 0.3 is the second one. So in this case, based on these two values, we will select only these two FFNs. And those are big, they are big ones. So we don't want to activate all of them. We want to activate one or two of them. And we will activate them based on this softmax probability at the end of the gating mechanism. So that doesn't cost us much, but but these ones are very costly. These ones are very costly, those are big layers. And we want to basically make sure that we only run a few of them. So this is basically this top one, top two routing. Okay. So let's kind of summarize what are the advantages. of the model. So specializations and interpretability. Those are the two things which kind of we can try to get. I mean, specializations is given. The interpretability, sometimes we can get, sometimes not. But here's an example from one of the papers, which basically looks at which tokens are routed to which experts. And they do see that there exists a form of specialization. So say in a given layer 2, there are routed tokens which are commas. Then say in the layer 3, there are basically articles and conjunctions. Then in layer 1, to some of the experts, there are some words. So we can see we didn't impose those specializations on the network. This is learned during the training, through the backpropagation, as we talked during the break with some of you. So the network basically learns, and those experts learn to specialize in, say, certain parts of speech, certain elements. So this is the advantage of the MOE, that we want basically the elements to specialize. We don't need the whole network if we want to just process the article there. We can just take part of it. So these are the advantages of the MOE. Then we have efficient parameter use, and this is probably the main advantage of the MOE, because at our disposal we have a huge model, which allows us, which gives us a very large capacity for learning. However, in the inference time, we only use part of it. So we use the parameters efficiently. We can scale a model to a very large size, but computationally, we only use part of it. We have this dynamic routing, which basically allows us this efficient usage. We have modularity and scalability, and that's what there was a question about, that we can maybe add or remove experts during the training by making models smaller or bigger according to our needs. There's something called KV cache savings. I'm not going to go into details, but if you are familiar with the KV cache, so there's as it was talked about yesterday, there are in transformer we have keys, queries, and values, and those are computed basically. They could be computed at every iteration, but for computational savings, keys and values are actually cached, and that's why it's called KV cache. So because we know what will be the output for the sum of the tokens, so we in the case of mixture of experts, we know which experts for a given token, basically the path. We know how a given token will be routed, so we don't need to repeat it over and over again. So in the case of the dense model, we have to save basically the values for all the activations. In the case of mixture of experts, we only save parts of the model. So this is also a saving. And okay, so this is this is something that Danda was asking before, and this is an example of how we calculate the parameters for the Mixtral 8 times 7b. We're not gonna go into the details, but basically here you kind of have a feeling of how big the experts are. So compared to the other elements of the model. So say embedding, which is traditionally a very big layer. It has about 130 million parameters. Attention is about 1 billion. Router, you see, it is tiny. It is tiny. It basically doesn't cost anything to do. It's a small router. Output is 8. In this case, experts. Input is the model, which is about 4,000. So it's the smallest part of the entire network. And then we have the experts. The experts basically they have a large portion, the largest portion of the model, which is 45 billion parameters. So this doesn't cost us much to run. But if we want to run experts, that would be very costly. And so this is so-called total parameters. In the nomenclature of mixture of experts, we distinguish between total parameters and active parameters. So the total parameters are the parameters from the entire network, and the active parameters are the parameters which are activated for a given input. So for this big model, which has about 47 billion parameters, only a small part of it, which is basically 11 out of 45, are activated. So this is the saving that we obtain from the mixture of experts. And then we will have a head which is also relatively small. Okay, so this is kind of a practical example of the mixture of experts in the mixtural model. Alright, so now let's go to the challenges of the MOE. So it's not all rosy. There are challenges, and there was a question about it. So let's dive into them. So in reality, if we don't take care of it properly, it can happen that we will have maybe 8 experts or 16 experts, but in reality only few of them, maybe 1 or 2, will be used. And that's something called expert collapse, and it does happen if we in a regular training, because of the way the experiment is designed, the architecture is designed. Only in this case, only how many experts will be more used in this case? 3, right? Yeah. So there are basically. So this is the actual load. So basically, the router will only give high probabilities to this 1, 2, and 3 experts. So no matter what input we input into the model, the router will tell us that we should go to the expert 1, 2, or 3, but we actually have 8 experts. So we're actually not utilizing the whole power of the experts of the whole architecture. So we will have to take care of it, and and how do we do it? So we will have this uneven token distribution, but ideally we would like to have it the way we have the red bars, not the yellow bars. Okay, so we do it through an auxiliary load balancing loss. Generally, that's kind of like a general note. In machine learning, the general setup of machine learning is that we are learning through computing certain losses. So, say in the case of classification, we can have a cross-entropy loss. And this is how it tells us that we are wrong, that we should improve. In the case of regression, who can tell me what is the most typical loss for regression problems? I hear square, L2 square norm, that is right. So usually there's L1 norm or L2 norm. This is a typical loss for regression problems. So, and no matter what problem in machine learning you will be dealing with, there will be certain loss when we are using the neural networks. So so basically each problem in machine learning has its own loss. Classification has cross entropy. Regression will have L2 loss. And in this case, we also use L2 loss, cross entropy loss, as a part of classification. Say if the problem is a classification, but it's not the whole picture. If we want to make our model do something, we have to basically design a new loss. And if you do research or if you learn machine learning, very often it's not emphasized enough, but losses is basically what makes machine learning work. And good losses basically what makes models work well. Then there is an optimization procedure, which is backpropagation usually, but if we backpropagate wrong losses, then the model will not learn. So usually in machine learning, if we have a problem, we need to mitigate it with another solution. In the standard machine learning, it is called regularization, where we add a certain element to mitigate this issue. So perhaps some of you studied, again, linear regression. There is something called the ridge regression, where we don't want the weights. If you didn't hear about it, don't worry about it, but just if you know about it, an example of a regularization is where we basically take a sum of the weights. We want the weights to be smaller in ridge regression, so basically we will take the sum of the weights, and if they are big, if they are big, then the loss will be big. If they are small, the loss will be small. So in regularization is a very typical way to deal with problems in machine learning, and this is also the way we deal with in mixture of experts by adding additional loss. I mean, it's very logical, but I want to emphasize it. So so in the case of mixture of experts, we do load balancing loss, where basically we have ideal distribution, which would be 1/n. If we have 4 experts, say it would be 25% each, and then we look what is the actual output, and then we look at the difference, and if the difference is big, then we will have a big loss. So ideally we would like to have a more even distribution of the, so this is the load balancing loss for the router. So we would like to have a more even distribution of the output of the gating. Then there is basically very similar loss called based on entropy. Have you heard about entropy? Yes. Okay, everybody or many people have heard about entropy. I will not spend time on it because we don't have too much time. But for some of you who haven't heard about entropy, it's basically a measure of uncertainty. So if we have a very even distribution, then we have high entropy, and if we have uneven distribution, we have low entropy. So these are examples. For instance, 0.25, 0.25, 0.25, 0.25. This distribution will have entropy 2, and another one, which is 0.5, 25, 15, 1 will have a lower entropy. So this is an important concept in machine learning, in information theory. So if you don't know it, make sure that you will learn it, because it will be useful in many areas of the machine learning. And for instance, here, this is a concept from information theory originally. It's called Shannon entropy, but we actually use it as a load balancing loss in mixture of experts. You would think that those two are unrelated, but they actually are. So entropy is very often used for losses in machine learning, and so I will not go into the details. You can see it on the slides, or you can just read it anywhere. Basically, it's a very typical concept, entropy, and I encourage you to make sure that you can actually compute it. So this maybe 1.85 is difficult, but this one you should be able to compute with pen and pencil, basically, because those are logarithms of the base 2, and you should be able to actually get those values. So I will not test you now, but somebody may at some point. All right. So this is our load balancing loss. So this is how we work on the output of the router. Then we have another. So we looked at the output of the router, but still, even though the distribution may be more even, but still some of the experts may be more overloaded. Still, there may be more tokens going to some of the experts. So in the literature, there is another intuitive solution, which is called expert capacity, which basically is that we limit the capacity of an expert. So if the expert capacity is free for one expert, if already 3 tokens, so what is mixture, was already routed to the first FFN, then that capacity is reached. So the next token off cannot go to the FFN layer. It will go to the 4th FFN layer. So this is something called expert capacity. There are some issues as a side note, because it can be like very often happens that if the capacity is reached for all the experts, then actually this token is routed to the next layer. It skips the layer. So this can be a disadvantage, and it has to be very careful about how we design this capacity. But that is not so relevant. It's just that the big idea is that we have certain capacity for each expert. Okay, so we had basically these 2 challenges about how we balance the experts. This is a very, very important problem and a key to make the mixture of experts work. Then there are other challenges and other solutions. There's something called a router Z-loss that is typically used. We'll not go into it, but if you ever work with mixture of experts, that's probably what you want to use. The memory footprint is something that the DB was asking. It's an issue that we do have to load the whole model into the memory. And then we also have a few parameters that we probably will have to tune, which is the gating thresholds, capacity factors, number of experts. So these are the things which kind of come together with a mixture of experts. Okay. So generally, I was talking here. I was trying to talk most generally, but I gave some probably more examples about NLP. More can be also used for vision models. You are definitely familiar with the vision transformers, where we divide the picture into patches and then we feed them into the transformer. We can exactly do the same thing for mixture of experts, only we don't feed the tokens, we just feed those patches, and it exactly works the same. There is a router, there are several FFN layers, and perhaps they have also some specializations. For vision, there are actually there are some additional works that look basically at the importance of patches, and in this case, it processes the more important patches first. And this way, if we have the expert capacity, which I just mentioned, it may be lower. So in this case, the expert capacity is 4, and then maybe some of those tokens could be dropped. In practice, it is often the case that the tokens are dropped. So for vision, there is certain priority scores are used, so that on first the more important patches are processed, and then if those the ones on the right, if only those patches are processed, we are still able to say that this is a dog, because these patches were processed. So it's actually very, very also efficient way to deal with images, because we only process parts of the image without needing to process the entire image. So MOES, it can be used for vision as well. All right. So we had advantages, challenges, and we will go to the last part, which is fine-grained MOE. And we'll talk a little bit about the scaling loss, which is, I think, also interesting topic with relation to LLMs. But maybe just, are there any questions at this point? Are there questions about the basics of the MOE? Yes, I can see there's a question.
Good afternoon. My name is Iswar Basa, and I have slight confusion regarding the export collapse. Is the export collapse because the dominant export which is being selected fails to launch the distinct features and launch the general features, or is it because of poor gating mechanism which is selecting the dominant experts at that point?
Very, very good question. It's a great research question, actually. You can probably research it. I would say it's more because of the poor gating mechanism. It's basically the gating that decides which experts to choose. So it is the gating mechanism that says, okay, we will choose the first expert, and we will always choose the first expert. So that kind of will be the result of the inference, and then the training will appropriately adjust. Like we will, as we talked about in the previous part of the lecture, only the selected experts get updated in the training. So if the first expert is always selected, always the first expert will be also updated. So the other experts will actually not learn. So that is another disadvantage. That we have the experts at our disposal, but they actually even don't learn. They probably will have some random weights because we always select this first expert. And this is precisely done because of the router. So the router will decide that we will go to this first expert. So that's why the losses that I just showed, the log basal lancing loss, but also there is another one called Z loss, they are applied for the gating. So we want to mitigate the problems from the gating point of view. So that is what we would target if we want to prevent the expert collapse.
So can I add a bit more? So if I'm understanding correctly, so if we regularize the gating mechanism, it also ensures that the experts learn distinct features and don't really it makes them not learn regular features so that only one expert can be dominant during the selection process.
If I understand correctly, the question is that if we don't choose the only selective experts, or if we choose all of them, then we will be able to, basically all experts will learn.
Experts will not learn overlapping features and learn distinct features.
Will learn distinct features, yes, exactly. That is kind of the purpose. Exactly.
Any other questions? Can you please ask?
So, could we also use experts of different parameter sizes so that some expert will do very complicated tasks and some will do very simple tasks?
Yes, right. I mean, it's a good idea, and that is a good segue to what I'm going to talk about. It's fine-grained MOE. In this case, we will not have experts of different sizes, but it is possible to have it. There are some works that do it, and I mean, there is no reason. I mean, okay, there is a reason to have it. But the reason is that it makes the problem or the architecture more complicated. How do we choose the sizes of experts? So this would be probably more complicated. That's why
we often go just for a simpler solution, which is each expert is the same. But the segue to this part of the lecture, the final part, is that we can actually have different sizes. So, did I answer your question?
Yes.
Okay, thank you. Okay, so let me just go to this part so that we basically finish everything, because it's also an interesting part, and I just want to at least just briefly mention it. This is also the part that my research group was working on. If you hear any lectures, they like to talk about what they do. So, let me just give a brief mentioning of this. But this is, I'll talk about general concepts which are behind it. Up until now, the MOEs, the experts that we worked on, they were the size of the original expert, the original FFN layer. So if the size of the original FFN layer was, say, 4,000, then each of them was 4,000, and that is still very big. Like they are big experts. And if we have, say, 8 of them, that's still quite few compared to all the concepts in the world that we have. Like only 8. So each of them still has quite a diverse expertise. So perhaps we should have more. But having more experts of a big size, it's infeasible. We cannot have so big experts. So what has been proposed, and what we actually proposed in our work, was to make them smaller. So this is the standard feed-forward network, where we have one big feed-forward layer. Just a simple depiction. Then in the standard mixture of experts, we would repeat this size, this big FFN layer into 2, and they are big again. And then we will round each token to a different one. So we have this small NLP that will basically direct it. But then they are big, so we could make them smaller. And that's basically how we make them. We will divide them. So perhaps you remember, I don't have a slide here, but the FFN layer consisted of 2 parts, of basically 2 layers, where the middle layer was quite wide. So what happens is, in mixture of experts fine grain, is that we will divide this very wide middle node layer into small pieces. So say if basically the width of the rectangle is the width of this middle the middle FFN layer, then we will just cut it down into maybe half or 4 or so on. This way we will have smaller experts. So as a result, the model will be more flexible. It will have more experts. If we have, say, 8 experts and we will divide each of them into 2, then we will have actually 16 experts. So there will be more flexibility that allows learn the model more diverse features. So this is the definition. It's a simple definition. DFF is the size of this middle layer in the FFN, and then the expert is just the number of experts. So if the FF is, say, 4,000, we have the number of experts, which is in this case increased, say from 6, and each of them is smaller to divide by 2, so 16. So each smaller will be 4,000 over 16. So it's basically just dividing them into smaller ones. And as you can see, this actually proves to be much more efficient than actually having big layers. So in this case, we call it granularity. So we have granular experts, smaller experts. And if we have 1,
Question to you, last question. For a dense model, so the one that we just talked about, what will be the granularity? 1, exactly. So this is the value basically by which we divide the original size of the expert. So if granularity is 2, so we divide the original expert into 2, into 4, 8, 16, and so on. As you can see, there is some saturation going on, but generally speaking, that there is a tendency that making experts smaller and more makes the model better. So, okay, so this is the fine-grained model. That's something that you may also use if you want to improve your models. And then very briefly, I want to mention about the scaling laws, because that's an interesting aspect of LLMs. So, the nice or the good part about the transformer, and I guess the element which makes them so powerful, is that they scale. So why newer basically GPT models? Why all the newer models are bigger than the previous ones? It's simply because the bigger models are better than the smaller ones, and our restriction is basically only the hardware. If we had more hardware capabilities, then we would build bigger models. This is not necessarily the case for convolutional neural networks. They might have some more problems, but generally it is the case for the transformer networks. That the bigger they are, the better they are. So there has been work on so-called scaling laws that show that transformer, they basically scale. So that as the size scales, as the size increases, then also the performance improves. And this is actually for a very particular relationship called power law, where basically the one it's a relationship between two variables where the alpha is constant, and we will basically scale. Say if alpha is say 2. Okay, sure. I'm finishing. I will go through it quickly. But just this is something. This is a school, so I want to kind of also teach the concept, because you can use it in other cases as well. It's a concept from physics. So if say alpha is 2, then we will have a relay, and x is the number of parameters. So then basically there will be a relationship that the loss will exponentially fall with or according to the power law with the number of parameters. So this is general idea about the power law, and it has been shown through the early works on scaling laws how the transformers scale. So as you can see that if we increase the token size, this is the test loss, and this is the token size. This is the test loss, and this is the parameter size. This is the training data set. This is the size of the model. If the size of the model increases, this is exponential axis. Here, this is also exponential or log, you can say. Then we will have here a linear relationship. So this means that we will have. This basically shows that as we increase the number of parameters, or as we increase the training data set, our model will get better. So that is what scaling laws. If you heard before about scaling laws, that is what scaling laws are. And this basically relates to the LLM models. And this is the form from the one of the original works, where basically we have the loss, and the loss is a function of the number of parameters and the training tokens. And these are some constants which we get. But the general formula is that you see This is the value in the denominator. This is a positive value. So the more parameters we have, the smaller the loss. The more tokens we have, the smaller the loss. This is the scaling loss for transformers. So the question is whether that works also for mixture of experts. And there has been work which showed that actually as we scale the model, the transformers, the dense transformers, so the ones which are not built as a mixture of experts, they will actually be outperforming mixture of experts. So as we go bigger and bigger, there was some work which showed that actually for very large models we should be using dense transformers. But it had made some not very great assumptions. For instance, that the data size is fixed. And actually, we showed in our work, it was probably the first work that showed that actually mixture of experts scales better than transformers, than dense transformers. So it shows that as we increase the size of the model, mixture of experts model, actually the model will get better, and even it will get better even more than the dense model. So at any scale, it is worth using the mixture of experts. So when we take, but this is the case for granular models. So if we make models, if we make experts small, so we take into account three parameters, three parameters: the number of parameters, the number of trading tokens, and the granularity. So these are the. Before the formula we had only two. Now we add also granularity. As you can see, there is a scaling law between the granularity. This is 1, 2, 4, 8, 16, and this is also the loss. So we show that the size, basically, we see that there is a power law relationship between the granularity and the loss. So this is another aspect of an architecture that follows the power law. So the power law is a very useful concept in machine learning as well, as it turns out, and in many aspects. So this is the scaling law that before you saw it only with N and D. Now there is also G. So this basically shows how the loss changes when we change each of these values. Those are the learned parameters, and basically you can see here that this is the compute budget. So if we have a certain compute budget, like this is for how long we will train the model, and basically this is the loss that we will obtain given this. So this is the loss that we obtain by using this kind of computational budget. So this line is basically the mixture of experts, fine-grained mixture of experts, and this is the line as a dense model. So as you can see that for every compute budget, the mixture of experts, fine-grained mixture of experts, will be better. And even better than that, for each compute budget, so this line is if this is the overhead, basically if this is just the fine-grained mixture of experts, this is mixture of experts but which is not fine-grained, and this is a dense model. So these are the three types of models that we can distinguish. It's the fine-grained mixture of experts. That was the last part of the lecture. This is the regular mixture of experts. That's what we've been talking about for most of this lecture. And this is the dense transformer. So that's the one where we have a number of experts equal to 1. So these are the three. And as we increase the computational budget, we keep getting more benefits by using fine-grained mixture of experts. So that is kind of the final point of this lecture. that fine-grained mixture of experts is something that probably you want to go for if you are applying mixture of experts in your field. So, as a summary, the key takeaways. MOE breaks a complex problem into simpler parts, assigning each token to a specialized expert. So we have different experts, different parts, and that's how mixture of experts gets its advantage. We use this gating mechanism, which, as we talked through in this lecture, it's a very key mechanism that has a lot of research is dedicated to this problem. It is a key component of the mixture of experts. And as a result, MOE provides large capacity efficiently. So large models become feasible because of these sparse activations, that we only activate parts of the models for given input. And then finally, that the fine-grained MOE outperform these models at any scale. So there's some further learning that you can do, explore more MOE implementations at Hugging Face. These are some of the most foundational papers that we talked about that you may look at if you want to learn more about MOEs. Also look at the implementation for more practical use. So thank you very much again. It's been a pleasure.
Hello. So my question is, if you are taking the context out of transformer, and let's say, for example, I have a brain scan, and I have an architecture which works on like the full brain scan, and another architecture which performs better on the partial scan. So if I have to like combine the two architectures, do I just put them in parallel with the gating mechanism, or what should be the strategy to like put an expression?
The question was if we have one model that works on a full scan well and then another model that works on the partial scan well, can we combine them? Yeah, I mean, why not? We can. I think generally, I mean, you can play with it as you want, and using a routing mechanism is, I think, here we basically talked about routing mechanism in the context of mixture of experts, but transformer mixture of experts, but you can use it for any other purposes. I think it's a very, very nice concept that can be used in research or even for like practical purposes. If you just need to basically appropriately train it, so that in your case, but maybe in some cases you want to use the partial one. In other cases, you use a bigger one or the one that processes the whole output. So if you appropriately train this router, this is of course possible.
So like if you just plainly put one architecture, another architecture, and just put a gating mechanism in front, then it would be efficient. Like there could be some other strategy to implement it as well. Maybe I don't know.
Sorry, can you repeat the last part?
So, like, could there be some other better strategy than just putting them in parallel and like implementing a gating mechanism?
Could there be?
So, like there are the two architectures, right?
Yeah.
So I could keep a gating mechanism on top of it, or maybe there could be some other strategy for more efficiently implementing the two architectures. Maybe.
You say that could there be any other ways to, instead of gating mechanism?
Not instead of gating mechanism, but like maybe keeping the gating mechanism in middle of the architecture or something.
In the middle of architecture. I mean, yeah. Again, it's up to you how you design it. In this case, yes, the gating mechanism is in the middle of the architecture. It can be in the middle. It can be before. I mean, one way would be you can train both models on their own, and then you can basically combine them into one by basically copying the FFN layers, for instance, from each of the two, and then you either freeze them or basically then you fine-tune the whole model just for a little bit. So you don't train the whole model altogether, only you basically initialize the model with the previous two models, and then you do some fine-tuning for the routing. So that's maybe one idea. There again, you know, there's no restrictions. There could be some others. So, okay. So perhaps we are out of time, but I'm here in case you want to ask me personally some questions or you're shy. And also, I'm unfortunately leaving tomorrow, so but I'm here today if you have any more questions. If you want later, you can also email me. There is this email, so feel free to reach out to me. And I think that's it. Thank you very much again.
Thank you so much, Kamil. And ladies and gentlemen, can we again please join our hands together for Kamil Adamezewski.
Hi, I'm Kamil, and I'm a speaker at ANAIS. I'm very happy and privileged to be here, and thank you for the invitation to come here to Nepal. This is my second time to Nepal, and I came here 15 years ago to work on a humanitarian project. Now I come in a different capacity as let's say as a professor, as a speaker. I am very glad to see I interacted here with both students and researchers, very diverse group of interests, diverse group of people, and I'm glad to see the enthusiasm of students who want to learn, and yeah, I wish all the students, I wish NAMI to further succeed in building AI here in Nepal. I'm always happy to assist, and I hope that it will benefit the students here, the whole community, and science and technology in Nepal that will basically improve people's life across the whole country.